Welcome to the Digital Amateur Television Experimenters Night. This is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania. Amateur radio is a worldwide hobby that has many different aspects. Digital television is just one of the many modes and areas that are covered. Maybe you're interested in becoming involved in the DATV Experimenters Nights. You realise that you do not have to be a radio amateur or need any ATV equipment to participate anywhere in the world. Also participate in the night by coming up to the Queen's Domain clubrooms. Yes, right on top of the Queen's Domain in the heritage-listed Coast Wireless Station. You never know, we might get you in front of the camera or behind doing one of the many roles during the night. We get underway with our program on a Wednesday night from 7:30 p.m. local time. We'll see you soon. This is VK7 OTC.
Okay, this is VK7 OTC, the club station of the Radio and Electronics Association of Southern Tasmania with our DATV Experimenters Night and VK7TW at the microphone tonight. And we've got Paul and we've got Sean and good pick up Sean on the Z90. Yes, it's a new model. It's a absolutely new model, but anyway, we'll get to that. I wish to acknowledge Tasmanian Aboriginal people as the traditional owners of the land upon which we present tonight and pay my respects to elders past, present and emerging, for they hold the memories, knowledge, culture and hopes of Aboriginal Tasmania. Yes, tonight, the precursor tonight is we have a little bit of a blast from the past. What's a good thing I can show here? The Zilog Z80. Now this is the Zilog Z80 Programmer's Reference Manual, and this is my my very well thumbed and very well annotated. There's lots of little pencil marks in this one. That I used back in the 80s and 90s when I was playing with Z80s. But anyway, getting ahead of ourselves. Just a quick bit of history. I started in IT back in 1982. And I know that seems an absolute eternity ago, but anyway, back in 82 I started with a little company called Microbyte Systems in South Australia in VK5, and we our claim to fame was we produced little interface boards, only quite small. And in fact, I think I showed one of those interface boards in a previous episode. It had an 8748 Intel microcontroller on it, and it went into a Triumph Adler daisy wheel electronic typewriter. And it was basically a serial or parallel, or IEEE actually. There was a IEEE interface that we built into the software, and it was a keyboard emulator. So what it would do was you would send code to be printed to the serial or the parallel interface, and it would print it out on the typewriter. So the typewriter would become your printer. Now, that was an Intel 8748. The computers we used at the time were CPM based. So those people who remember CPM, CPM. Yeah, hold that thought, Sean. Hold that thought. CPM on Z80 machines running 64 kilobits of memory. The CPM on those machines enabled us. We had programmers that were connected so that we could program the 8748 microcontrollers. Can I just say they are a pain in the backside to program. They use plus and minus 5, plus 12 and plus 40 volts to program them in the right sequence, or else you brick them. And we that's what we were using. That was the technology we were using at the time. The company that was next to us in the same building was servicing BBC computers for schools. So that's the sort of era we're talking about here. The Microby, the Z80 computer that I was using was a Dick Smith Super 80 computer, if you remember those. So there you go. Now, computers were very new at the time. They were very new to me. I learnt, and the interesting thing here was I learnt, and here we go, Sean. This is my very, very well thumbed, and in fact the front cover's almost coming off. This is my very well thumbed Rodney Zaks book. Now, Rodney Zaks' claim to fame was he produced a whole lot of programming manuals. One of them was a Z80 programming manual, but he also produced, at the beginning of that, From Chips to Systems, an Introduction to Microprocessors. So this is, I bought this book, and I spent a lot of money buying this book, and I looked inside and it said $26.50. So back in 1982 or whenever it was, that was a lot of money for a book. And this book took you through computer architecture. I noticed that there were a few post-it notes still on here. System components. It went through. Hang on, I'm just going to the fundamental concepts, the internal operation of a microprocessor, the system components, comparative microprocessor evaluation, and this takes you through the Z80, the Intel, the Motorola architectures, etc., the Newman machines, the Harvard machines from memory, etc., etc. System interconnects, the applications, interfacing techniques, programming, assembly language and high-level programming, system development, and the future. And it's the appendices here. This shows you the era. Motorola 6800, the Intel 88 instruction set, and the IEEE 696 S100 bus signals. Now, we actually had an S100 bus system from the Smoke Signal Broadcasting Corporation, and I really, really wish we had kept that particular machine, because it would probably be worth a fortune these days. But it was an S100 bus machine. It had 8-inch floppy disks on it, so it had the princely. It had a memory system. No, Sean, there isn't. However, my favourite magazine at the time was Byte, and Steve Circassia used to write a column in Byte that I used to read religiously. And so they... and in fact, I should have bought it in. I ended up buying, there were magazines that were sold with Byte that were Steve Circassia's articles all put into one magazine, into a particular book. And I bought that book, and I did build quite a few things out of that book. So there you go. And that's Byte magazine. So there's another blast from the past that I totally forgot about. Thank you, Sean, for reminding me. And yes, Clive Sinclair used the Z80 in many of his computers, the ZX80, the ZX81 and the Spectrum. And if you happen to have any of those computers, please keep hold of them, because they are wonderful machines, and they're actually worth a lot of money these days because there's not that many of them around. So, anyway, back on track. The Z80 architecture. Now, the Z80 architecture was produced by a company called Zilog in Silicon Valley. Chaos Manor. And the Z80 architecture was a very accessible architecture. In fact, let me go to, let's see if this works. Okay. There we go. Now, we have the same problem. That doesn't seem to pick up the changes. Just let me try this and see whether we pick... there we go. Fantastic. Okay. Now, if I push the magic button, it doesn't do anything. But if I push the magic button on here, that's a bit better. Now, the Z80 architecture, for those who haven't seen inside a central processing unit, a CPU, they're very similar. They're slightly different architectures. The Z80 architecture had on the left-hand side, in the surrounded by the dotted line, there is a whole lot of there's a control section, or the microcode that actually runs the CPU. It contains program counters and all sorts of stuff in there. It contains the way that it controls the internal movement of data and addressing around inside the CPU. There are a whole lot of registers, and you'll notice that there's a WZ and a WZ complement, the little one next to it. There's the B and C registers, the D and E, the H and E all registers. Now, each of those are an 8-bit register, so they have 8 bits in them. They make up the 16-bit registers. So this is an 8-bit CPU. Its internal architecture is 8-bit. It has 16-bit addressing available to it, and so most of these registers have another 8-bit connected to them to give you a 16-bit address space. You've got IX and IY, which are the index registers. You've got SP, which is the stack pointer, so where within programs you can make sure that the stack pointer's pointed in the right direction, to the right register or to the right bit of memory. And then you have the all-important program counter, or the PC, which is a 16-bit register as well. Now, the program counter is literally where the particular line in memory where the CPU program is up to. Very important to maintain the program counter, and you can increment and decrement the program counter so that you can jump to different parts of memory and different parts of the program, etc., etc. So that's the center bit. There are the two muxes that go into the internal data bus, the 8-bit internal data bus. They're multiplexers, so it enables the transfer from those registers out onto the data bus, so that it sends it to different parts of the CPU. There is the arithmetic logic unit, the little V on the right hand side. So this is how it does calculations, how it does its mathematics, its binary mathematics. There is a temporary register in there. There is the A and the F registers and the complement A and F registers. There is the accumulator, so this is where it does its addition, subtraction, etc. And that is all a separate part of the CPU die. And then you've got at the bottom side of this diagram, you've got your 16-bit address bus, and then you've got your control bus, which is all your control signals, so that the timing is correct. This is where your clock signal comes in, all of your control signals for the peripherals and the memory, etc., etc. All of those go off to the other peripherals that are available to you. So let me go back to here. So that's the Z80 architecture. Now there are there's two types of processors that were produced at the time. There is the CISC processors, which is the complex instruction set computing. So this is where you have a CPU that has an instruction set which is greater than 80 or 100, I think it was something like that. So it's greater than 100 instructions, and that's why the programmer's reference manual has all of those instructions and which registers you have to load before you run the instruction, and any conditions that you have to set in the flag registers, and etc, etc, etc. So that's what the programmer's reference manual is all about. There is the other processor that was produced at the time is a RISC processor, or a reduced instruction set computing CPU. Now this has somewhere between 30 and 80 instructions, so a reduced number of instructions that are optimized to run on that particular processor and run fast on that particular processor. So if you had to do an addition or a subtraction or something like that, what you had is really, really fast addition and subtraction instructions, and you would just run them the number of times that you had to run them, and they ran quite quickly. They'd run in a cycle or something like that. In the case of the Z80, the Z80, original Z80 ran at 4 megahertz. So cycle times were at the time pretty quick, and many of these instructions only had 1 or 2 cycles that it actually had to do for it to actually undertake that particular instruction. So, and you'll notice in the manual you'll find here. I'll give you an example. What's a good example? Oh, here we go. Here's the load. Let's go to there. I think that'll get us there. Now, if I zoom in here, this is the programmer's reference manual. These are load instructions. Now, load instructions are pretty simple instructions. You can see load HL. So this is load the HL registers. So this is a 16-bit register. You load it. There are flags that are set when you do the load to make sure that the load actually has completed properly. These are the flags that come up, and each of these flags means something different. The opcode. Now, this is, if you're in assembler, you're actually loading in assembler. This is the opcode, the 8-bit opcode for that particular instruction, for that particular. This is the mnemonic load HL with NN. It is the hex, that's the binary, that's the hex of it. The number of bytes that you need to supply is 3, and the number of cycles, memory cycles, is 5, and the number of T states, which is 16 4 megahertz periods, whatever 4 megahertz, the period of 4 megahertz is. If somebody wants to do that calculation for me. So this is literally the instruction, one instruction after another. These are all the load instructions. Then there is arithmetic instructions. There is these are arithmetic and program instructions. These are interrupt instructions. These are jump instructions, so you can jump around inside the program. This is adding and subtracting from the program counter, etc., etc. So this is the programmer's reference manual. for the Z80 computer. And there were a whole lot of other components that were also available here. There was not only the CPU only enabled you to actually run those programs, but the CPU was always connected to a range of other peripherals. So those peripherals included, there was a counter timer circuit, a CTC, and I'll show you one of these in a sec, in real life. There was a parallel I/O, which was a PIO. This was a dual 8-bit 2-port, so there were two 8-bit ports as part of the PIO. There was an SIO, a serial in-out. So this was your like a UART. So this would provide you with dual channel synchronous and or asynchronous serial communication at a particular baud rate. You'd set the baud rate, you'd set the stop bits, you'd set the parity bit, etc. And you set the handshaking and all of that. There was a direct memory access controller also, which was part of the Zilog chipset. Now, a DMA controller, or a direct memory access controller, when you had most memory back in these days was either dynamic memory or it was static memory. Now, the difference between dynamic and static memory, you had to refresh on a regular basis using the RISC and CISC, so the row and column access signals, and there was a timing that you had to do to basically refresh what was in dynamic memory, because if you didn't refresh it, the memory contents would disappear. And so there was RISC and CISC timing, and what the direct memory access controller enabled you to do was actually supply those RISC and CISC signals to your array of dynamic memory chips. And so it took care of all of that. It would also do things like block moves within memory and all sorts of things. You could hand it off to the DMA controller and it would do it really, really quickly, much more quickly than the CPU would do. So that was the chipset, if you like, that was around for a Z80. The Z80 was the 8-bit controller. There was also a Z800, which was a 16-bit version of it. There was a Z880,000, which was the 32-bit. Just let me look this up to make sure I'm getting this right. There was a Z80, a Z800, a Z8000, and a Z80,000 that was produced. And the funny thing about this was I have a Zilog data book, which I happen to keep hold of, which is dated 1985, and this is all of the this is pre-internet, so this is how all of your data came. Zilog would produce this. If you were buying them in quantity, they would throw these things at you, and it goes through the Z8 family. So the Z8 family, and I'll go into the Z8 family in a minute. The Z8 family was the Z80 microcontroller, so it had a whole lot of peripherals built into one 40-pin chip, and I'll show you one of those and an application for one of those in a sec. Then there was the Z80, actually there was the Super 8, which was a beefed up version of the Z8. There was the Z80, which was by far the most popular, the Z800, which was the 16-bit, the Z8000, which was a 16-bit with, I think, slightly more addressing, and then the Z80,000, which was actually a 32-bit processor, so way before its time. And this was all at around the time that Motorola was releasing the 68,000 and that sort of thing. So, but anyway, this goes through all of the timing. I'll show you what's in one of these manuals. All of the timing, if you needed to connect this to different peripherals, external I/O and memory timing. It had all of the, what the ports did, what all of the bits did within the processor, etc., etc. And it went all the way through all of your timing, the Z80 bus request acknowledged cycles. It went through all of your specifications, all of the voltages, all of the inputs and outputs, all of the timing, etc. So these were the Bible if you were a developer for Z80s, and well, any any sort. Intel produced theirs for all their Intel, and I have some very old Intel ones as well, because we were still using the 8748s for a long time. Then there was Zilog also produced the Z80 Assembly Language Programming Manual, and again this is a very well thumbed and very well annotated, and you can see here's the that command I was talking about earlier, the opcode. This is the load HL register. You can see the opcode format. It is this and the register number. The description, the contents of register R, which is specified here, are loaded into the memory location specified by the context of the HL register pair. The symbol R identifies registers A, B, C, D, E, H, and L or L, assembled as the following opcodes. It had 2 memory cycles, 7 T-states, and at 4 megahertz, it was 1.75 microseconds that it took to execute that particular command. Control bits affected were none, and then there is an example. If the contents of register pair HL specifies memory location 2146 hex, and the B register contains the byte 29 hex. After the execution of load HL into B, so the contents of HL into B, memory address 2146 will also contain 29 hex. So, and this is every opcode and how you use it for assembly language programming. So that we're not talking high-level languages here. We're talking. This is talking about hexadecimal coding, and that's what you used to do. If you were lucky enough to have a compiler and an interpreter, then you might be programming in, I don't know, BASIC or heaven forbid Pascal or something longer. So so there you go. And you're spot on, Sean. There was a DART, a dual channel asynchronous receiver transmitter, and there was a fully synchronous a receiver transmitter planned by Zilog but cancelled due to the noise it made. Well, there you go. So SIO and a DIO, the asynchronous and the synchronous serial controllers. Spot on. So now, okay. Now, one of the things, and I'll show you. This is came in a. I've still got the box. One of the things that was produced in the 80s was the Microprofessor. Now the Microprofessor was a Z80 based teaching resource. You can see here's the, and I'll show you this up close and personal in a minute. It came in a little case that you could put on your bookshelf. And the Microprofessor, if I plug this in, let's go here, go out to wide, and plug it in. Comes up with Microprofessor 1. And if we zoom in, I'll just zoom in here quickly. I was just going to show you down here the keypad. You can see there was actually a tape interface I realised on here. There is the audio input and audio output up here next to the regulator, which gets bloody hot. The audio input and output that you enabled a tape interface, so you could record to a cassette tape or a 1/4 inch reel-to-reel tape. But this enabled had a reset button, goes to the monitor. So there is a monitor built into this particular. Now all a monitor is it's a program that runs in the background and enables you to enables the functions for things like the keyboard and the program and all of that sort of thing. You can cause a manual interrupt. There's a user key that you can program here. Move, install. There is delete. There is step through the program. There is go to a particular setting.
go to a particular register. So this is the program counter. Now the program counter is currently set to 0637 in this memory, in this ROM, and the value, so this is address and this is data. So the address is set to this, and what is in that particular memory location is 10. Then on the white keys you've got a hexadecimal keypad. Now for those who don't know what a hexadecimal keypad is, hexadecimal is a base 12. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. That's the base 16. Sorry, base 12. What am I thinking? Base 16. So you represent numbers. Literally can be a particular number or a letter from A through F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And that's 16, obviously 16 numbers that are represented by numbers and the first 6 letters of the alphabet. So everything's entered through hexadecimal. You can see there is an alternate function for each of these keys, which is to get to the registers and the complement registers in the Z8 architecture. And now, the chipset I was talking about. I'll point at these. They're pretty unassuming, but here's your Z80 CPU, 40-pin dual inline package. Here's the PIO, so the parallel in-out, which comes out to these connectors. This is the CTC, so the counter timer circuit. There's a color burst crystal here, which is the crystal oscillator, and some logic which comes up with some latches and also the oscillator for the clock signal. There's the EPROM, which is also contains a basic interpreter. Now the basic interpreter, when you go to that particular part of the memory, then what you've got here is an overlay for the keypad, which gives you the basic commands, which enables you to get to those particular basic commands within a keypad. You've also got, there is not dynamic memory on here, there is static memory. This is a 16K static memory chip, and then there is an 8255. Now this is, the 8255 is like the PIO, but it has 3 8-bit ports that come out on this particular chip, and they all go to these pins along the side here. This is a little breadboard area which enables you to prototype particular logic here and then drive it with your 8255 IC here. There's a speaker. There's one of the output pins is driven through a transistor to drive a speaker, and then there is also some of I think the PIO, the 8255 output is used to multiplex the LED displays, and they're multiplex. Now on the other side here, I don't know whether I can do this. On the other side here, I can see that. There is the display format, which shows what the particular commands actually mean, because it comes up in short form on 7-segment displays, and it gives you a bit of a key. You can see here, I've got something stuck on here, which is the flag register in the CPU, the Z80 CPU, and what each of those flags actually means, so that you could then do a mask on those flags to find out what if you did arithmetic, it was sign, if it ended up as 0, if there was a half carry, if there's a parity overflow, or add and subtract, or there was a carry where you had to do another function for the arithmetic. So there you go. So this is the MicroProfessor, and the MicroProfessor came with the plug pack, but it also came with the basic control and how to use BASIC in the MicroProfessor. It came with experimental software and hardware and a whole lot of things that you could do, including
including all of the source code in assembler. So here's an example. You've got your location in memory. You've got your hex that is representative of what it's actually trying to do here. And these are programs, binary to BCD conversion programs, and all sorts of things. So this was the experimental manual, software and hardware. There was a user manual. There was a user manual that showed you how to use the keypad, etc., etc. And then there was a listing of the monitor program, which is what's in ROM on here as well. So there you go. that's the MicroProfessor, and this is how I learned all about Z80 processors. Very well thumbed keypad. Didn't really get into BASIC terribly much, but most of it was assembler. And then I managed to get there were some compilers that were available on the Super 80 that I had, and that was just that just absolutely took off. And I was when that took off, I just the compilers were fantastic. I could go to macro languages and all sorts of stuff. So anyway, now hello Andy, hello. And there was also the Jupiter Ace. Yes, there was. And Steve Circassia, How to Build a Z80 Computer, has been released as a PDF. Yes. And in fact, there is quite a few Hackaday and Instructables and a few others have how to build a Z80 computer. A sort of a bit of a blast from the past. So there you go. And a sad ALU with multiply or divide. We have to say it's so easy these days. Yes, it is, Sean. Well and truly. Lionel, hello, Lionel. Base 12 mathematics is used in some remote parts of Tasmania in comparison to base 10. Used more widely. I love it. And so that was that's the Z80. Now, the company I work for, I mentioned Microbyte Systems, went on to produce. Now let's see if we can do this. Let's zoom out. Can we zoom out any more? We can. Okay, we went on to produce what we called the Glass Typewriter, which is funnily enough is what teletypes used to be called. And the Glass Typewriter still used the Adler typewriter as the keyboard and the printer, but it also used a screen. And you had floppy disks where you could save your documents and then obviously edit them and print them and do all sorts of things. So it was a word processor. This is a couple of prototype boards that I kept hold of because we were playing around with particular designs, and you'll notice the power connector here has moved. And it moved to here. It was a much better way of doing it when we were designing it. But this is one of the prototype boards. You'll notice, I'll point out, there is the PIO, the Z80 PIO, which goes to the parallel port here. We put a Centronics connector on there for those people who remember Centronics printers. We put a Centronics connector on there. There was also here was the floppy disk controller, the Western Digital floppy disk controller, ST506 interface. ST506 was hard disk. That came later. It was another standard. We've got a Western Digital display controller here, and you'll notice that there is an EPROM just here, which is the character generator EPROM for that particular display controller. That came out on a little 5-pin DIN plug that went off to a composite monitor. There is the CTC, so the Zilog counter timer chip. There is the SIO2, so this is the serial in-out, and there are serial RS-232 drivers, transceivers here. There is the EPROM for the program. There is the CPU that's here. There is an 8257
8257. Now, what's an 8257? That's just gone from my mind. Sean, can you look up what an 8257 is? An Intel 8257. That might be a hard disk controller, actually. It might be a hard disk controller. We might have got the hard disk controllers on here. You'll notice here is your memory, your dynamic memory here. There are 8 4164s at 150 nanosecond access time. This is 64 kilobits of memory. There is a whole lot of logic, glue logic around this, and also between all of this. But anyway, it had a Apple compatible power supply, Apple IIe compatible power supply. These are the serial ports. There's a reset button on here. So this was a Z80 based word processor board. So that's a bit of a blast from the past, and that's one of the prototype boards. There's no silk screen on this board because we were debugging the board at the time. But this was one of the prototypes that ended up with me for whatever reason. So that's what we used to do, and we used to then debug that. I was product support manager at the time, so we were looking at those boards and making sure that they were up to scratch before they were put in machines and then sent out. So there you go. Now, I mentioned the Z8 microcontroller. If I go to, let me try something here. If I go to, let me walk around here. If I go to, now, let me zoom in here a little bit. What you are looking at here is a little board that I made up when I was at Microbyte, which, that's a bit out of focus. Let me pull out a bit. Okay. Now, this is a Z8 microcontroller. So what a Z8 microcontroller is basically a cut-down version of the Z80 CPU. It has some parallel ports on it. It's got a serial port on it. It's got a little counter timer. It's got an interrupt controller on it, and a few other bits and pieces on it, all on one chip, or 40-pin chip. There's a couple of latches here, and then there is an EPROM. And the EPROM contains the program. This does the latching for the address, the addressing to the EPROM for the Z8, and you then have a whole lot of I/O ports that you can use. So this is a little board that I made up, a little universal board that enabled. This was put into quite a lot of test equipment that we built to enable us to test all sorts of things. But one of the things that I built back in the day was what we affectionately called K9, with the and yes, it was the Doctor Who reference, and this was a little autonomous platform that enabled it would run around the floor, and when it hit particular things, these are the little bumps that are on there. There's a micro switch on here. There's bumps on all sides. And then there is, these are two geared motors, 12-volt geared motors, and there is a little photodiode LED arrangement here, which is a stall detector. There's a little gear in here that breaks and opens the little optics, the photoelectric cells that are in here, and tells whether the motor's stalled or not. So it tells whether it's stalled, it tells whether it's bumped into it, and it goes through a little routine in the CPU to try and get out of a situation if it bumps into things. So anyway, that's the. I'll switch it on off the. Oh, and there's over here there is a little tone generation circuit in here, which there's a speaker on here. So when it you can see as it bumps into things, it goes through a particular routine to get out of it.
you can let that run around on the floor. It's got a 12 volt SLA battery, 7.2 amp SLA battery, and it will run around. On the front, just hang on, I'll switch that off. On the front, there is a little, actually there's a ball race in there. There's a ball bearing race in there. There's a little wheel that runs around and turns around and enables it to go in all sorts of directions as it flies around the room. So anyway, this was originally an 8748 microcontroller, and I changed it over to one of these prototype boards when we were playing with the Z8s. But anyway, I'll take this out into the club rooms later and let it run around the floor and see whether it can get itself all screwed up. So anyway, that's the Z8, and we're talking about here the mid 1980s. So this is and it's actually survived that long. I haven't ripped it apart and made it something else. DMA controller, 8257 DMA. So that was a cheaper version of a DMA controller than the Z80 version of the DMA controller, which was quite an expensive chip at the time. So we used the Intel DMA controller instead of the Zilog DMA controller. That's exactly right. So there you go. Thank you, Sean. Thank you very much. So how are we going for time? Oh, we're way out of time. I might leave that for next time. One of the things now there is. We finish off with. Why does it do that? We finish off each week with a space weather report. So our space weather report for this week, it does have a HF fade out warning. That is HF fade out warning. Is that going to give it to us? Oh, that's not even going to give it to us now. Oh my goodness. Okay, let me just try that again just to make sure. And nope, it's not going to give it to us. Okay, that's all right. There is a HF fade out warning for the 10th, 11th and 12th. R1 activity, chance of R2, so it's not that much. HF fade outs are possible if comms are difficulties are experienced, try a higher band. That's the only warning, because it's been quite stable over the last few weeks. So, which is doesn't bode well for the weekend, because the weekend is the summer field day, VHF and above field day. There'll be a whole lot of people out. So please, if you're in Tassie or eastern seaboard of Australia, we will be out. Murray and Richard will be up on the mountain. I'll be down at Eaglehawk Neck, and there'll be a few other people who will be about and around. So that's the field day. Now we've got coming up, we've confirmed a couple of other presentations. So the 7th of February, Greg Bird from Surf Life Saving Tasmania will be giving us a presentation around their radio network, their extensive radio network. February the 18th is the AGM and SGM and barbecue, free barbecue. And then on March the 6th, we've got Mars Butfield Addison, who is a PhD candidate at University of Tasmania and works also at the CSIRO, giving us a presentation on space junk and the role of amateur radio. So that should be a fascinating presentation night. So anyway, that is your blooming lot for this week. Lots and lots of. Now I expect you to all go home and bone up on your Z80 microprocessor architecture. No, I'm joking. Anyway, have a good week. 73. We'll catch you next week, and we'll have some more fascinating bits of history and technology to wow you with. So 73, and we'll catch you next time.